What happens if memory becomes huge and persistent and we basically collapse the memory hierarchy? And I've been interested in that for a long time.
Shaheen and I immediately said, well, that's HPC, right? And so that's been the position that we've taken for years and years. And we've seen that the HPC community has embraced that. And they've embraced AI as a very major workload that they need to include in their complement.
The synergy between AI and HPC is really quite interesting. I continue to think AI is a subset of HPC, not something separate, but in the enterprise world and in the market, it's sort of having its own identity, and HPC now becomes like the foundation of AI in some ways. If you want to build an AI team, you're going to go hire HPC people and buy HPC gear to do it.
Welcome to the OrionX Download. This is a podcast where we discuss and simplify the big ideas in technology that are changing the world.
Hi everybody, welcome to another episode of OrionX Download Podcast. Today is very special for me because now I have two of my colleagues with me. Steve Perrineau, he and I have done a whole bunch of crypto-oriented and quantum-oriented podcasts in the past, and Adrian Cockcroft, who just joined us a few short months ago, having spent 5 years at AWS, and before that at Battery Ventures, and before that at eBay, and before that, I'm going to let us go back to our backgrounds in a bit. But this one is going to be about supercomputing and about system architecture. It's something that we all have touched over the past many years. So maybe we can start by asking you guys to spend a minute or two talking about your encounters and history with supercomputing. So Adrian, you go first, and welcome to the podcast.
Yeah, it's great to be here. So I was always a performance specialist, and I was a performance specialist at Sun, and then some point about 2000, 2001, and I worked with Shaheen on and off, knew Shaheen through the various things we were doing at Sun, but ended up as the chief architect for the HPC team in the early 2000s, working for Shaheen. And had a good time. We were doing fine. Sun, unfortunately, wasn't doing so fine at the time and was shrinking.
Right.
And at some point, the parent organization that we were working for shut down, and we kind of all got sent adrift. So I was having a great time. I think I keynoted Supercomputing Phoenix '03, I think it was, for Sun, and learned a lot. So basically, as we were all laid off. I went to eBay for a bit and Netflix for a bit, and moved much more into the horizontal scale commercial, customer-facing, direct-to-customer business. And then gradually moved to AWS about 6-7 years ago, and was really focused back on the enterprise space again, and was always interested in HPC, and it was always sort of a side thing, and there were some things going on around it, and gradually seen the use cases building out in cloud. So happy to be back in that world. And then last November, Shaheen and I went to supercomputing together and just wandered around the halls for Shaheen introduced to all these people. And we went to a bunch of things, and we went to the Kennedy Assassination Museum. And it was a cool time to spend together in person and to really immerse myself back in. And then I wrote this blog sort of as part of a reaction to that, which we'll get to.
Yeah, that sounds good. Yeah, you never quite left HPC, which was delightful for me to see. Steve, you and I go even farther back, so remind us of your encounters and where you got the HPC bug.
All right. Well, I started to get the HPC bug in the mid-1970s when I did my thesis calculations on one of Seymour Cray's control data machines, simulating X-ray emission from clusters of galaxies, their cosmological evolution. And I left astronomy in 1980 and moved into the supercomputing world at that time, starting out in a software development position with British Petroleum in San Francisco. We were modeling Prudhoe Bay, this giant reservoir on the north slope of Alaska, where occasionally lately the Air Force is shooting down objects. And spent a few years there. We had our own controlled data vector supercomputer. And then the geologists had a Cray machine. They wouldn't let us use it. So when the reservoir side wanted to do modeling on Cray for compositional simulator, we ended up buying Service Bureau time. So that's when I started using supercomputers in the cloud. That was from UIS in Kansas City. You now know them as Sprint. And I became more familiar with the Cray at that time and the Cray sales guy locally. And so I ended up moving to Cray in 1983 as a system analyst and sales support role. And so I worked with a variety of vendors, Cray 2 Tours of Duty, Sun 2 Tours of Duty, SGI, and Alliant, in a variety of technical marketing sales roles. And you and I overlapped because of my second tour of duty at Cray, which was in the early 90s. I got my exposure with Alliant to parallel computing. They had this very nice 8-way parallel design and then later a 28-way. Unfortunately, they picked the i860 chip from Intel.
Yeah.
Their second generation, and that was kind of the end of the company there. So I returned to Cray and was actually put into a sales overlay role supporting the lower end of the product line, which were the baby vector machines and then the super server machines that you were working on, Shaheen, up in Portland. So that's when we got to know each other. And that was in the early to mid 90s. And then after a year at SGI, after the takeover, you dragged me over to Sun.
I did, yeah.
And then I spent most of the next 13 years at Sun up until 2010 and a year after the Oracle takeover. And I moved with them out to the Asia Pacific region based in Singapore and was leading our business development for high performance computing sales across all of Asia Pacific at that point.
Yeah, great team
And
there.
then I did, it was time after the Oracle takeover, they decided they weren't going to be in the HPC marketplace. And that's when I hooked up with you again.
That's right.
OrionX.
That's right.
One thing we didn't talk about, back in the 1980s, I was working on a massively parallel supercomputer thing, like a transputer array of 64 processors per board. And Myco ended up with the IP when this company called Niche died. But for a while, I was trying to get a geologic simulation thing working on a massive array of machines that had about 1 megaflop each. It really wasn't vector. There were lots of these little things client to click. So there was sort of that one little bit. So there's the massively parallel stuff. I probably have more ancient experience from 40 years ago in massively parallel. But these things come around, so you just have to wait long enough, and whatever technology you learned 20 or 40 years ago will become current.
I am so delighted to be reminded of Niche because I had forgotten it, and I was at the time at Floating Point, so we were doing the T-series that was also using in-MOS transputers.
Yep.
And John Gustafson was like the chief architect for that system at that time. So just learning Occam, and I think they had a development. I think there was a system called Occam Development System that people would disparagingly called odious.
Yes. Yeah. It was, so there was a few things there. One of the, we don't get into this too long, but there was no way to debug anything and there was no error handling. Other than that, it was fine. So if you're every now and again, your program would just go wrong and you go like, oh, okay, let's stare at it and see if we can figure it out again. But it was, if you got it working, it worked pretty well. But anyway, moving right along.
That's right. So one thread in this conversation is system architecture. And I think the history we just heard from each other is tracking what changed in the industry. So supercomputers are vector instruction sets and vector architecture, and the beauty of vector was that they were all specialized processors with vector extensions, and the compiler knew about it. The memory was shared and it was easy to program. And if you could get performance out of it, it was a dream and continues to be very, very effective. And Intel's AVX instruction set, Sun, I think, may have introduced that concept with the visual instruction set VIS way back when. And then all the other supercomputing vendors, CDC, Hitachi, NEC, they were all vector until massively parallel computing came about. But the other thing I wanted to mention, because I think it's relevant to culminating with Adrian's paper after SC22, was the heterogeneity of the system, that coprocessors started happening. I was at IBM using floating point systems, and then at FPS itself, where we had a attached processor that was essentially a coprocessor accelerator for its time, even though it was 2 cabinets big for 19 megaflop kind of a machine or something, 38, something like that, if I remember correctly. So fast forward to GPUs that, hey, I have this graphic accelerator. Why can't I use it for simulations? Well, you can't because it only does the 4x4 matrix multiplies really well. And it's kind of like a systolic array. But, if I can tweak it here and tweak it there, maybe I can use it. And then after a while, why don't we make it 64-bit? And after a while, why don't we add some RAS capabilities to it? And then that kind of led to AI explosion, was ready to greet AI explosion. And then suddenly we realized that maybe we don't need 64 bits for AI. That 32 bits, 8 bits, 4 bits, we can do with fewer bits and make it go faster because memory movement is expensive. And if I can cut the precision, I can double the memory bandwidth effective to my application. And then you do a massively parallel. And then how are we going to connect them? What glue am I using to connect these things together? What is the viscosity of that glue? Is it Ethernet? Is it InfiniBand? So these vectors are all coming together. And then you walk the halls at SC22, and we started seeing some patterns that I think led to, Adrian, your paper initially at Inside HPC, and then later on in your Medium channel. So let's tee that up a little bit, Adrian.
Yeah. So back in the 90s, Sun had some machines with some non-volatile memory in them, so the high-end servers, and that non-volatile memory like fixed a whole pile of problems. Just a little bank of unvolatile memory. And I started looking at, okay, different types of memory. And then over the years, I've been going, okay, hey, why don't we have non-volatile memory? And then Optane almost happened and then sort of didn't happen, and all these things going on. So I've been tracking for a while this area of what happens if memory becomes huge and persistent and we basically collapse the memory hierarchy. And I've been interested in that for a long time. And I started calling it petalith architecture because you could get a petabyte of memory and it's not big data if it fits in memory. So I just like redefine petabyte scale problems of data problems as being not big data anymore. Because if you can fit it in sort of one machine or one address space. So that Optane didn't really happen partly for a number of reasons, but one of them was that it was sort of Intel proprietary and the people didn't want to get kind of locked into that ecosystem and it would only work with certain CPUs and things. So there was sort of a reset that happened with all of these next generation buses. And what happened, I mean, there's obviously a lot more detail here, but what effectively happened was everyone got together and said, we're just going to pool all of our IP and resources and come up with one standard that isn't tied to any one chip, and that's CXL. And so I started tracking a little bit about CXL. And one of the things we looked at supercomputing was, we started seeing CXL and asking people questions about it and asking sort of the logical next steps. Where does this go? And the thing is, going back to the old things, like you can make a system call to move data to another machine. That takes tens of microseconds or hundreds of microseconds. You can do it in a user level library and memory things sort of using sort of the InfiniBand model. You can get down to somewhere in the single digit microsecond level for a sort of round trip. But if you're doing cache coherence, you're sort of at the 100 nanosecond level. It's maybe 150, maybe 200, depends how far you're going. But it looked to me like the latency for getting something from one machine to another with CXL is roughly arm wave, order of magnitude lower latency for moving something. And there's a whole bunch of algorithms which are just latency sensitive. Because that's kind of what scares you. And it's not all of them, and there's tail latency, a whole bunch of other things. But it seemed to me that if it got used right, then you could sort of replace a bunch of the different layers that we have, like InfiniBand and some of the networking PCI bus, those things. You could put it all on CXL and start aggregating large amounts of memory in a rack together, moving things around. You get a more flexible architecture that you could reconfigure using the way CXL sort of layers everything out. So we walked around, we talked to some people, we found some CXL switches, and it was clear that we were sort of in the middle of the emergence of CXL, and it's another year or two before it's going to be like the 3.0, which is the one that does fabric management, was the announcement of the standard was the middle of last year. And the actual rollout of it is going to be another year or two before the silicon happens and the architectures happen. So the theory I was sort of floating was, so what happens when CXL meets high performance computing? And we wandered around and talked to people about that. And that's one of the core ideas in this blog post, was just asking that question, what happens?
And the other thing that happened after SC22 was the paper that Satoshi Matsuoka and Thorsten Toffer wrote and instigated a big discussion in the community called 12 Myths and Legends in Supercomputing. And it was their very nice way of talking about topics that need discussion. The HPC world has always been good about getting to the point. The presence of standard benchmarks that cover every exercise, every muscle of a system, and they are reported on and analyzed is an indication of that. And some of the new technologies really don't benefit from that. So let's talk a little bit about that in that context too. How do we see supercomputing systems morph into a new architecture?
I think it's the applications, isn't it? And maybe Stephen can talk a bit about this, because there's some applications work well on massively parallel, some work well on vector, some slosh data around non-locally. So I think the Holy Grail kind of thing was an architecture that would do good at everything, and you can always specialize. So the question really, I guess, is what classes of applications are working well on different architectures? And what we're seeing is that the AI machine learning training and inference is a new application that's come in, which is starting to drive hardware to optimize for it. And then we look at all of the other weather simulation and finite element and geospatial,
Right.
all those kinds of things, or astronomy or whatever. There's all these different workloads. And one of the sort of key things to understand which workloads work well on which kinds of machines and which ones map to which benchmarks. So maybe that's a good topic for a bit.
Yeah. Well, we've seen this picture before with the rise of massively parallel computing. And I want to say in the larger context that we've always had this tension and trade-off between going wide and going deep. And that going wide and going deep applies to the individual processors, as well as how many processors you have. So vector is deep, parallel is wide, for example, oversimplifying a bit. We had in the processor design, we saw the tendency towards superscalar architectures. So for a while they were saying, we'll do VLIW instead of going deep with vectors. And then you get the same issues around memory and how you interconnect to memory as well, right? How do you structure your memory hierarchy and so forth? How do you share memory once you've got more than one processor?
And things like hyperthreading, which have been annoying and gradually seem to be going away again as we move away from Intel onto. So that makes things easier in some ways.
Another way of going deep. So
yeah.
I think it'd be interesting to just look at the first 4 myths. I think we can dismiss one of them very quickly, but because they kind of hit you hard right up front. Their first 4 myths are about 1, quantum computing, number 2, deep learning, number 3, leveraging Moore's law forever, and number 4, accelerators. So the first one, I think the quantum computing one, we can probably dismiss fairly quickly, at least between Shaheen and I and probably Adrian, that what we've seen so far in quantum computing has been very highly specialized, and mostly it's been toy problems that are trying to do highly specialized things as well. So we're seeing at the current level of technology, toy problems that have potential and that they tend to be quite custom towards these architectures. And the proponents of quantum computing are not arguing that they have general purpose solutions. So more and more we're seeing that it's going to be in the role of sitting in the supercomputing center as an attached processor, as an attached asset that people can share. And the sharing also comes about because of the exotic environments that are required for most of these, where they need cooling below liquid helium temperatures. But I think the second one is a much more interesting discussion. Myth number 2, everything will be deep learning. I think as we saw the rise of deep learning solutions with neural nets and very deep and complex and hierarchical neural net architectures, Shaheen and I immediately said, well, that's HPC, right? And so that's been the position that we've taken for years and years. And we've seen that the HPC community has embraced that. And they've embraced AI as a very major workload that they need to include in their complement. But it brings back these same issues of wide and deep. And now they go in the precision. How deep do you go in precision? Can you do it in 16-bit? Sometimes you might even be able to use 8-bit arithmetic. Mm-hmm. And so we're seeing architectural design move towards a higher performance for shorter floats and for shorter integers.
Yeah, we're particularly seeing that for inference, right? So a lot of the time in training, you need the extra precision to just because you're still exploring the space, right? So then once you've trained a neural network, you can then condense it and get almost all of the accuracy at much higher speed by reducing the size in the right way. So that's where I'm mostly seeing sort of these inference-focused engines. And then you can argue, is most of the workload inference or training? And if you're looking at one of the big speech recognition systems, yeah, there's a lot of training there, but most of the activity is, I won't mention any of them by name because it wakes everything up, right? But you know who I'm talking about. But most of that, what I've heard is inference. Whereas if you get to some of the more specialized things, it actually is like that people are spending so much time on training and then they're retraining so often that the inference is actually still catching up. It'd be interesting to know what the ratio is for something like ChatGPT, right? Like how much compute time are they actually spending on inference versus training for those? And how does that blend? And so people are building very different hardware for those two environments as well.
Yeah, well, in general, I see AI as being such a vast, new, fertile ground that is going to have many, quote, killer apps, and each of them justify custom silicon fully optimized for that particular app. And if you can do that, then maybe life is good. And I think that's why you're seeing literally tens, if not, over 100 chips being developed for various aspects of it. But certainly the precision that Steve you raised is a very important part, because it is definitely influencing HPC folks to revisit whether they really need all that precision that they thought they do. Because for a long time, I thought that proper error propagation analysis had been done to indicate that indeed you need 64-bit precision. And for some applications and algorithms, you kind of know that you do, but maybe you don't. And more applications are learning how to do that. And then maybe use some AI algorithms to get to the same answer, or to get within shouting distance of it, and then use traditional models. So the synergy between AI and HPC is really quite interesting. I continue to think AI is a subset of HPC, not something separate, but in the enterprise world and in the market, it's sort of having its own identity, and HPC now becomes like the foundation of AI in some ways. If you want to build an AI team, you're going to go hire HPC people and buy HPC gear to do it.
One of the challenges that we heard a bit about at supercomputing is they can't keep their grad students, because you've got somebody that's trained up in an HPC environment and they go off and become an AI engineer, machine learning engineer, and make a lot more money. So there's a sort of brain drain problem.
That's right. That's a big problem. Yeah. So now you have to really talk about why working in that HPC environment is valuable beyond just the money part. But the money part sometimes is really hard to say no to. Yeah. So back to the architecture of things.
You know from your FPS days that, there was a lot of usage of these systems in 32-bit mode for signal processing. The geophysics community, they've always run their algorithms in 32-bit mode. But we know that if you're running complex magnetohydrodynamic solutions, that 64-bit sometimes isn't enough. You mentioned John Gustafson. I mean, John Gustafson has proposed alternative arithmetic,
right,
where you actually have 3 fields rather than 2,
right,
in order to give you precision where you need it and to be more efficient. And actually, that efficiency could play all the way down in the low precision end.
That's right.
With the deep learning side as well. So it's a very broad landscape from 8-bit up to 64 and above, and you just have to look at your applications and your algorithms and do your tuning. I think the next one was, well, I'll quote it. The success of GPUs, growing demands for lower power and highest performance, and the end of Moore's law created a myth that future supercomputer architectures will be just like smartphones with multitudes of hardware customization. So I'll throw that out to the group.
We were in one of the panel sessions, and there was a question of whether the next generation, the current generation of supercomputers are built out of Intel and AMD mostly. And then there's a few ARM-based and things like that, which are sort of seen as exceptions right now. And the response we heard from Stage was they thought it was too expensive to stand up a team and build your own chip. And they were saying hundreds of millions of dollars or something like that. And Shaheen and I kind of bounced that around a bit and said, we don't think it's that expensive, because there are startups that haven't had that much funding that have built chips. And it's probably more in the tens of millions now to build a chip. And if you're building a machine that's costing you a huge amount of money, why don't you just design the CPU chip to have all the 64-bit floating point vector memory bandwidth, magic extra interfaces to whatever you want, and you just lay this out. And if you've got whatever 2, 3, 4 and whatever it is nano processes to go build this out of, you end up with these monstrous chips. So that's one thing. The other thing that's really changed in the last 20 years is like getting a chip to work when we were back at Sun took years. Like you get this damn thing and it didn't quite work, and you tinker with it, and then you'd have to try and get it into production and get the volume. And we were talking to somebody, the guy used to work at Google, and he says he built 10 chips at Google, and if they didn't work first time, something was seriously wrong, right?
Yeah.
And we're seeing that the custom ARM chips being built by Apple and Amazon and Google and everyone else, they are pretty much working first time. So the chip design technology is now so mature that you're simulating that pretty much you're assembling these incredible chips with, I can't even remember what the latest number is for transistors. Probably get several zeros wrong because I'm old and I can't remember how big they are now. But the ability to get it working first time and have a monstrously powerful chip. Like if you look at the difference in the Apple M1 or M2 chip and the AWS Graviton chip, they're roughly in the same technology. There's roughly the same number of transistors, but they are built very differently. One's a server chip. It's got a lot more cores. The Apple one has a big GPU and tensor and all that kind of stuff, tensor units things. So it's got fewer cores. They're playing around this different memory bandwidth, but those are just built on basically the same core, the same ARM core.
Right.
but very different. So the idea really here is that when you look at the next generation, it'll be ARM or RISC-V or something. Someone will just go and build monstrously good chips and just sell them into the HPC community. And there's a few companies doing that. Isn't there a French company? Do you remember what their name was? Shaheen's always good at remembering the names of all these people.
Yeah, that's kind of, I try to remember the history and the names and the players and all that. Yes. So there is Cypearl, I think.
Yeah, Cypel. I think that's
yeah.
the one I was thinking of, where it
Yeah.
seemed like they were doing something similar. So that was an interesting point, and there's sort of a division of like, which way is that going to go? Is it going to be good enough to just take whatever Intel and AMD decide to give you, or are people going to get a lasting advantage from having something much more custom?
Yeah, and the other thing that's happening is chiplets, and if the future of chips is chiplets, and now building a chip becomes basically the logical equivalent, if not the physical equivalent, of picking off of a menu and laying it out on a just giant substrate. And now you can say, I want 2 of these and 3 of those. And suddenly you have a highly heterogeneous, but highly customizable and low cost way of producing chips that are really good just for what you want. So the networking, the GPUs, the precision, the Biren chip that was announced last year at the Hotchkiss conference, and it's in China. So I think it's having some difficulty getting manufactured now with TSMC and such. But that one did not have a 64-bit support at all because it was focused entirely on AI. And I think their take was, if you really, really need 64-bit, I bet you can just simulate it or come at a different angle. So that just indicates the plethora of options that are out there and how you can assemble them into just what you need. And my take is that the HPC market has enough sway in the market to get what it wants, highly optimized for what it wants, and doesn't have to compromise and say, well, I got to use a chip that's really designed for online transaction processing because that's where the market is. So that's the other thing. Now, with all this technology, something has to connect them all together. And I think that's where the PCIe CXL discussion comes in. And I think one of the theses of your paper was this emerging new capability for interconnect that sits between CPU buses and InfiniBand, and it's based on PCIe.
Yeah, it's sort of rack scale. It's designed to go 1 to 2 meters.
Right.
The bandwidth it's 4 levels. I forget exactly what the term was, but the bit transitions go between sort of just on and off. There are 4 different levels, so they get double the rate per pin, effectively. And the bit rate's up. So I think it's 64 gigatransactions, and they're sending 256 byte, or roughly flits, which is the unit. So it's sending fixed size chunks around on this network. And that's PCIe 6 already has all that. So given that physical transport for moving these 256 byte chunks of things around, in what CXL does is it adds cache coherence on top. And now in that 256 byte thing, you've got some extra protocol, but you get like 200 and something bytes of payload, and the rest of it is error checking and stuff like that, a bit of addressing and whatever to make sure it gets to the right place. Then you hook, and these are point to point. So the way the connectors work is you have 2 connectors, one going one direction, one going the other direction. So you can pump data in both directions at the same time. And I think it works out, I was trying to figure out how many gigabytes per second it was, but it's a good amount of capacity per CXL or connection. And the thought was that a CPU design would have 2 or 4 of these built into the CPU, as well as the memory bus. And then you can use that to connect to a switch or to remote memory. And with CXL 3.0, what they've added is fabric management. So there's 3 variants. One's an I/O mode, which replaces the PCI bus stuff. You're talking to network adapters or whatever, or you're talking to other CPUs. So you'd use the I/O mode probably to replace RDMA-like things. Think if you want it to look more like an InfiniBand kind of replacement, you could do that. And then there's a memory protocol where you can basically have a big bank of shared memory in the middle of your rack and have all of the nodes share access to that memory. And so there's some interesting architectural things here. If you look at the current Cray design, they've got a fixed size board with setup. There's a sweet spot that they've decided to build on, but you can't, if you need twice as big or half the size or something, you're kind of fixed, right? What CXL lets you do is sort of play with the size of that sweet spot of what is the clump that you want to have that is memory coherent, and what do you want to have that is on a message passing. So you can play games with that. I think that's going to be an interesting to see how that plays out.
I think that's huge also because you are now you are now having requirements for a lot of processing capability at the so-called edge. Not exactly the far edge where the door sensors and temperature sensors are, but at the near edge where you can have a, suitcase size, if not a, small box size, what you see on a cell phone tower, that size of a box. And if you have a content delivery network, if you want to do some AI filtering closer to the scene, that's a very suitable place to have a bunch of GPUs and CPUs. And then you have to worry about the environmentals and, is there too much heat and humidity? And what if it rains? What if it's too hot, right? So that basically means that you've got a confine that you need to fit systems in. And you may not have the luxury of using a really large. So you may have to make do with what size of a board is available, and using this technology to strap them together and glue them together makes it possible. So I think that's a big use for the so-called edge data center.
Yeah, I mean, that's already happening a lot, right? The thing that you can do here is you can aggregate the memory together. And this is where, it would be nice if the memory was persistent, but even without persistence, you've got many terabytes, hundreds of terabytes up to sort of, and this is why I call them sort of petalith. It's sort of a petascale monolith. The idea being that your future architecture is going to look like a rack or a half rack of CXL clump with a network between those clumps, rather than current mode where it's sort of the units are much smaller. So we're going to have a much larger endpoint, which is memory coherent and running at much lower latency for transfer rather than the message based. And you can leave something like, the other thing is if you're sharing a big block of data with somebody, you send all the data over and they don't use all of it, they use some of it. You didn't know which bit, so you had to send it all, right? So this way you can just put it in memory and say, it's over here. And you go, I only wanted these 3 bits out of that. You don't have to send a megabyte to somebody where they only wanted to use a kilobyte.
That's a really good point, yeah.
So there's a bunch of things where if we rebuild the applications in the right way, there may be some interesting optimizations. Yeah. Lots of cool stuff coming.
Very powerful. And of course, this is one of the myths on Matsuoka's list of 12 myths. So I'll just give you a little bit of the counterpoint and then you can address that. It was their myth number 8, everything will be disaggregated. To stop the waste of memory resources, the academic community is advancing on the silicon photonics front. Industry is pursuing scale-out technologies such as CXL, cache coherent interconnect for data centers. But a few players seem to push the idea over the edge with their plans to disaggregate everything. We see 2 remaining challenges for broad adoption of all optical interconnects: low-cost manufacturing and optical switching. So what do we think about those points?
We did see someone, wasn't there? There was somebody, we saw a few vendors at supercomputing. And it's always one of those things that's coming soon, not quite here. Just like persistent memory or whatever. So one day there'll be a system with persistent memory and optical interconnects. And maybe we'll still be around to actually see it.
And there will be fusion energy as well.
Oh yeah, running on fusion energy.
And a small reactor, small modular. But, Satoshi actually mentioned that this is the kind of technology that's been coming for a while. My understanding is that the companies working on optical networking at that level are still really working on individual links to try to make those work. There was a good announcement today from IR Labs that is make some breakthroughs with their wavelength modulation. And then similarly with Avicenna, that they also have a chip-to-chip shorter range optical networking. So a lot of progress is happening. A lot of VC money is going into these things. But just like PCIe 6 and CXL, it seems like it's a couple of years away. But when it does look very promising. It is going to be on the order of 10 nanoseconds or less. So it's kind of game-changing technology. But then switching does remain to be done, is my understanding. Maybe some people are making progress too.
And it's more circuit switching than packet switching, right, for the optical. That seems to be kind of the idea of it, right? Because if you got a circuit, once you've set up the circuit, the light's just going to get there, right?
It's driven by telco requirements, right? So.
Yeah, that's a useful model for thinking about it. But I think this fallacy thing, I don't think disaggregating everything, the myth, that's right, getting the myth down to, I don't think we disaggregate everything to be too small. I think it aggregates together. What I'm talking about is a larger aggregate that's flexible. So one of the things in CXL 3.0 is it's got fabric management, which means it's dynamic, which means a running system can be reconfigured. Its memory and connections can be reconfigured without having to sort of stop the machine, reset it up and reboot it. And there's shared memory in there. So you've got multiple machines with truly, cache coherent shared memory between them, pools of that, with the ability to reconfigure those on the fly. The fabric management for that is going to be entertaining, and I'm sure there's going to be some interesting crash bug problems. It's like, I'm trying to debug this machine, but the machine no longer exists because it got reconfigured somewhere, But assuming they can get that to work, I think there's going to be probably in some ways a different model, because if you reconfigure your machine halfway through a run, I mean, if you look at some HPC workloads, they aren't constant workloads over time, right? They move through different phases. Maybe you actually reconfigure the machine for different phases in some way.
In fact, there are those who do that. Although if you have a machine that can be split up into different systems, then you might just be able to do it under one copy of the OS, especially if you have shared memory going. Yeah. So you kind of go right back to the old SMP days where a lot of things were simpler, and maybe we go back to that. I think the other angle with aggregation is that what exactly do we mean by disaggregated? Is it just the kind of fabric that connects these things? Why do I care whether something is physically on the same board or not? It all depends on what connects these pieces together. And if that connection is going to give me what I need, then I don't really care where physical packaging is. So
I think the last myth is one that we might want to address.
Sure, let's go.
12. All HPC will be subsumed by the clouds.
All right.
There you go.
That's good. Okay, so that actually ties into the last thing I wanted to put. I spent a bunch of time at the AWS booth and had a good chat to Brendan Buffler, who's one of the lead guys there. Really, really good guy. And he sort of explained a few things to me that I really hadn't understood before, which is the way that networking works in the cloud, particularly on AWS with their Fabric adapter, is quite interesting. So rather than sending a large block of data to the other node over a path, where you establish a path and you send all the packets in line, and it's in order delivery because that's what TCP/IP does. What they're doing is actually multipathing and doing out of order in the middle. So at each end, it looks like a TCP connection, but in between, it's actually multipathed out of order with extremely fast retry. So what they're doing is collapsing the tail latency. There's no head of line blocking if anything goes wrong. And they're using the fact that the environment in the cloud is over-connected. They've got way more paths per node over the network. So it might be 32 different ways to get from one machine to another. And they'll just put all the packets out 32 wide across whatever connections they've got and retry any that didn't arrive and just don't care about the fact that they didn't arrive. And at the other end, they sort of reassemble it into something that's in order. So that's the EFA sort of model. And I really hadn't figured that out. There's a few things about it. But what it means is that even though the EFA, because it's Ethernet-based, its minimum latency is sort of in the 15 microsecond kind of level. Its tail latency for large transfers, or real world, I'm sending a megabyte or I'm sending a few kilobytes or something, or tens of kilobytes, is actually better than, in many cases, than InfiniBand or something like that. So are you sensitive to the minimum latency, or are you sensitive to the tail latency? And one of the reasons that some workloads seem to be working better than expected on cloud once you get it all sorted out is it's actually tail latency that matters. And we also see that in the Cray interconnect has also got a lot of extra optimizations for tail latency. So maybe that minimum latency doesn't matter as much, which lets you build machines which are actually bigger physically. You can spread them out more as long as you've got enough paths to send everything in this multi-path model. Anyway, so that's kind of one of the little tweaks that's a little different between cloud and the way that a typical data center or a commercial system would be built.
So I think one of my walkaways at SC22 was that the presence of this kind of an optimization on Ethernet, driven by how the cloud guys are doing it, and then emergence of PCIe 6 plus CXL is really showing a world where you might just be able to do PCIe inside a rack and do super optimized Ethernet across the racks. And that may very well be the standard networking fabric of the future for a good while until this silicon photonics stuff is going to come in. And that would be a competitive challenge to InfiniBand and other sort of protocols that are in there, except that they have the benefit of legacy. They have the benefit of all the drivers are there, all the optimized, and they could also participate because many of them can do InfiniBand as well as Ethernet. So they're really not relying on that. So it's not like a threat to the vendors themselves, but it could be a challenge to the protocol, let's say.
Yeah. I kind of summarize it as will CXL kill InfiniBand. And I'm not sure if we really went with that as a title, but that was sort of, I think it was one of my early titles for this. I was trying to get, it's a bit more provocative. So maybe we call this little get together we've got today. We want to stick a big target on it.
There you go. Now, as it relates to HPC applications all going to the cloud, I do not see that. I believe that on-prem has a bright future for itself, because you kind of need cloud in the picture, but not exclusively. And I think many companies are going to have that, and significant cloud growth like crazy, but also growth on the on-prem. And then also when it comes to national labs and other national initiatives around the world, one of the very objectives is to learn how to do that stuff. So even if it might be a better thing to go in the cloud and do it, that's not the point. The point is, can you build this? And well, I'm going to have to build it before I learn how to do it. So let's go do that. And I think the exascale projects are very much important from that standpoint. So you have that kind of skill set within the mission that you need.
One just little comment on that is the cloud providers are designing their own chips. And if one of the cloud providers really gets deep into an HPC specific chip, they've got the dollars to go do something and do something extreme. And there may end up being a little sort of cloud provider arms race amongst themselves to build systems that actually are just built out of chips you can't buy for your own data center. And so,
right on. Yeah.
But that's a possible. It might be a few years before we get to something like that. We're already seeing some signs in that direction. But yeah, I agree. There's always going to be a mix here. But the thing is that we're seeing more workloads working better in the cloud over time. And it's just going to chip away at different pieces of the system as that happens.
Right on. All right. Well, thank you everybody for joining us. Thank you, Adrian. Thank you, Steve. I think it's wonderful to have all three of us here and all of you in the audience. So please keep in touch with us and do all the right things, share, comment, etc. So until next time, when we might go to fusion energy next time, right? Because Steve, you wrote a paper that's doing also very well. And it's a topic that I wanted to touch for the past year or two. So I'm delighted to have that opportunity. So we'll schedule that in the coming weeks.
Okay, great. Thanks. It's been fun.
Take care all.
It's great to see you two again.